Well, it's good to see you, CEO. You've all made it from your various travels and joined us here for yet another World Conference. The objective of WCEAM is really to bring all of you together, really to advance your knowledge or the body of knowledge in engineering asset management. I wish you all the best, enjoy your sessions, and I'm sure there'll be plenty of discourse and discussion. Having said that, I'd like to introduce Professor Kari Koskinen.
It's a great pleasure for me to welcome you to this World Congress of Engineering Asset Management. We are very happy to have this opportunity to arrange this conference. And with the word, I mean both TUT and VTT. We are separate organizations, but we have very close cooperation in many fields, and this Congress is one excellent example of it. Keynote presentations, and the first one will be given by Dr. Kari Komonen from Finnish Maintenance Society.
I think that we are also cavemen of asset management. Because I think that at the management level, we don't use all the opportunities we have. We are cavemen. That's my topic. But I'd just like to say that in order to save billions of euros or dollars or pounds or any currency, we have to totally revise our thinking within physical asset management. I think that even the accounting methods we are using in companies and organizations are old-fashioned. I have one very naughty question. Net present value, so what? I've been reading quite a lot of papers, and it seems to be so that if you use net present value, then you have done something which is correct and sufficient. But there's no how to say, reasoning and no thinking why we are using it and how we should use it. For example, what is a proper interest rate? What is a appropriate lifetime for various elements of calculations, for various items? What is the uncertainty linked to various elements of calculation? So that's why I finished my presentation saying that we have great opportunities to improve our asset management. And we have tools. The world is full of tools, and we don't use them. And they are simple ones. It's easy to learn them in one day. Believe me.
The next speaker will be Professor Gianta Lianas from University of Stavanger, Norway.
Let me start quoting a statement by the Investigation Committee for Columbia Shuttle disaster in 2003. Complex systems almost always fail in complex ways. And this has a very intimate connection to what we call as laws of change. And it has two basic attributes when it comes to change: control and uncertainty. As Joe said, in Industry 4, we step into an era of what we call as transforming assets. We do see some major developments in transportation sector. We're talking about ultra-modern transportation. We've got next generation aviation and defense systems. We've got intelligent oil fields. We also do have telemedicine applications. So industry is stepping up towards Industry 4 and some of the dynamics around that. If you look very closely to these trends, there are some key features of this what we call as an engineering bubble. The first and foremost is got some compounded complexity because of competitive innovation. And it's going to be very agile and spontaneous. It's very much risk inviting. And it displays a certain degree or high degree of uncertain behavior. The type and the linear school look for very known patterns. And because of that, it operates under very predefined boundary conditions. It's got to be risk aversive. We try to impose regulations and we try to look for predictable behavior and traceable failure mechanisms. And we are familiar with all those stuff around it. However, the loose and complex school, in contrary, has to be operated under different principles due to highly uncertain dynamics. There's a risk appetite growing. There's a self-regulating mechanisms to govern those systems. The behavior is very agile. At the same time, it has very complex failure patterns around it. So it does not imply that we should throw away all the good work we have done. We are not going to throw away all the rules and skills we have built centuries and decades, but use it as a very solid foundation to build a strong knowledge domain that helps us coping with the uncertainties in future.
But the focus in the industry has shifted from the products quite much to the solutions and services. So that is what has been ongoing for some time already now. Different companies as well as research groups are thinking about those aspects. And for example, in Finland, the FIMEC research programs SWEP and S4 Fleet are thinking about those and driving the Finnish industry further with. The other trend is the sharing economy and asset-light kind of thinking. That's way how quite big part of the industry is thinking at the moment. Couple of examples like Uber as the biggest taxi company in the world without owning any of the taxis, or Airbnb as the company who is leading accommodation provider without any of the real estate. Caterpillar is trying to do the same for the heavy machines with their yard truck concept. Another example is mobility as a service, which is aiming to utilize better the transportation methods, cars and public transportation, combining those with the good service rather than physical products. So asset-light or minimal physical asset way of thinking is very big trend currently. Big question is actually, who wants to own physical assets anymore?
My talk is more going to be focusing on a specific aspect of asset management in the area of dynamic model of a specific mechanical system. But eventually, to make sure whatever the simulation methods we generated can be utilized, we need to target the potential field applications. In field application, we say if you have a gearbox, whether it's a fixed shaft gearbox or a planetary gearbox, we usually use the sensor data to collect vibrations or acoustic or other data, then utilizing that for us to diagnose or assess possible deterioration that is experiencing inside the system, as the system is utilized to deliver its function. So we imagine that's what we needed to do in field. So what can we do in dynamic model, in simulation, in theoretical investigation? Planet gear, I can consider, there are 8 gear pairs, the sun is measured planet 1, planet 2, planet 3, planet 4, and planet is measured with the rain and so forth. And we can consider for every gear, whether it's sun gear, planet 1, planet 2, planet 3, planet 4, or even the rain gear, or even the carrier, we can say for each component, it has the horizontal possible vibration, planet direction, or vertical direction, or rotation direction. For each one, we can say we have X, Y, Y, theta 1. So we can look at that.
Gonna go. So thank you so much. Thanks for taking the time to be with us over these last 3 days, and I wish you all well. And surely we look forward to catching up again in Chicago.